So I'm not very familiar with the Zoom. Okay. Right. Um, my presentation is about the theoretical foundation and the multiphysics modeling and artificial intelligence for smart geotechnical engineering to enhance the resilience of large cities. So my name is Xiaohui Chen, and I'm an associate professor in geotechnical engineering, and I'm an academic leader of geomodeling and AI group, and I'm from University of Leeds. So my presentation, I will firstly talk about the challenge for the resilient cities, and then move to the theoretical part, and then talk about the modeling, and finally have a discussion on artificial intelligence and introduce my team. So if we think about what are the challenges to big cities, of course, we have to link it with flooding. And if we think about if we are going to develop some ocean city, the water aspects are highly related. For example, the seawater and also the pollution generated by the cities, and that links to chemicals. And also, if we are going to build on the city in ocean, which means we may have soft clay, and we have to build a foundation over there, which is a part of underground aspects. So all these are the challenges during the climate change crisis, and there's external pressure on all these aspects. So if we think about the environmental, city environmental, we may have the groundwater pollution and the soil restoration we need to care about. And in terms of the underground city, for example, Hangzhou, and they have a plan to develop an underground city. So basically, for such kind of underground city at the global climate change crisis, and there's quite a lot of uncertainties we have to deal with. So that all these are the challenges from either from water, from chemicals, from the infrastructure. So these challenges, if we can link them, maybe we can confine them in the multiphysics model and in porous media or in fracture media. So I'm going to talk about the theory for the coupled process in porous media or fracture media. And classically, we may have geomechanics to study the deformation, stress, and the displacement change of the soils. And we may have environmental geochemistry focus on the water aspects, investigating the pollution and the chemical reaction. We have environmental mineralogy to focus on the mineral evolution process in a longer time scale. And also we have the geomicrobiology to study the bacteria. So that all these are our classic and traditional disciplinaries. And the question is that this mixture is actually a system. And because of our history of the scientific study, we separate them into different components, but we have to keep in mind it's a system. And all this system, we may have strong interactions between each other. For example, if we simplify to make a mechanical for soil deformation, hydro for water, either surface water or groundwater, chemo for chemicals, for chemical reaction, mineral evolution process, bio for bioplants, for the plants and for the animals, and also for the bacteria, and the thermal for temperature. All these processes are closely integrated together. And we cannot just use one disciplinary to investigate. And do we have something we can use to study the system rather than rely on different disciplinary? For the resilient city, if we think about the picture here, if we have water, and the water will have an influence on actually the deformation of the soil and the rocks. And the deformation of the soil and the rocks in return will have an impact on water transport. The temperature may have an influence on chemical reaction, and the chemical reaction may have an impact on the water transport as well. And also for temperature may have a direct influence on the deformation of soil and rocks. So all these are very closely integrated together, and we name it as coupling. So coupling means we have different components and they are closely engaged with each other via a dynamic process. So our research question is that can we have a unified theory to describe the whole system in order to reach smart control and the design of such kind of system? So the unified theory is trying to cover all these aspects together. And that is what my team has been working in the past more than 10 years. So why do we need such kind of a new approach rather than we pick something from chemistry, pick something from microbiology, and pick what we need from the geomechanics? So why do we need such kind of a new approach? And we put the name of the approaches as mixture coupling theory. So there's a big difference. So you can see this looks like an apple and orange. It's a combination approach. It still have a shape like an apple, but it's a dead thing. It's not organic. It's not an organic component. But for a unified theory, it provides structure for you to explore. For example, if we recall Newton's theory, and the Newton's theory can enable us to explore in different aspects, for example, continuum mechanics, for example, water movement, and for example, the aerodynamics, all this, if we found the root, that will be Newton theory. So that is the difference between the unified approach and the integrated approach. A systematic approach from the approach we have been trying to focusing on is from published comments is a systematic approach which can help build a coupled mathematical model based on a single unified theory based between geophysics and the chemistry and between multi-scales. So that is why we need such kind of approach. Before we talk about this project, and I'd like to mention a movie, and I guess some of us may have seen this film before. It's Talent. So basically, if we look at the words, we have TE and the reverse upside down TE at the right, and in the middle we have N. And there's an important concept, even for this picture, there's people moving forward, and the people backwards. There's an important concept in this film, which is entropy. The entropy, and what is entropy? And why entropy is important. When we talk about entropy, I would like to show another picture. This is the first ever black hole. And for the black hole research, and we all know Professor Hawking from Cambridge made a great contribution in the black hole research. And the entropy can be used for the black hole research. But what's the link of using such kind of concept into our soils, microbiology, and mineral process? So let's have a look about the what is entropy. Entropy is the universe driving force of change. You guys come here to listen to me, blah, 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 blah. You have a driving force. Either your boss is here, either you are interested in my presentation. All these are different driving force. And we can always interpret it as entropy. We work hard every day because we have a motivation and to get more freedom, either financial freedom or more freedom to explore the world. So that is why we work very hard. And we have a driving force. In nature, the same things. For example, we have a highly ordered components, and they all fight for freedom and increase their freedom. Therefore, the entropy increased. If we think about the soil and the rock system, on this picture, we have solids, we have water or chemicals inside, and there may be some strong interactions. All these are about freedom change. Even for chemical reaction, they are freedom change. So therefore, entropy can be used as a foundation for the mixture coupling theory because it describes the dynamic process, that freedom change. And the entropy change links to the energy because we need energy. So from the mathematical point of view, the mechanical deformation of the soil and the rocks, we can use energy because that is energy form. We have influx and the efflux of fluid mass. So that is energy we can integrate. And also the dissipation process generated by associated with entropy. In this different form, we can include as many forms as we want for different components. We can get a balance of Helmholtz free energy. And therefore, we obtained the energy in this system. And also to describe the different relationship of the flows, because we have water flow, and the water flow may have the driving force from chemicals. And your motivation come to listen to me, blah, blah, is not just about, maybe not just about one driving force, and maybe by multiple driving force. So therefore, we have J1 to Jk as flows, and we have F1 to Fk as driving force. In this matrix, we have F1, F2, and Fk as the major driving force, but also we have side driving force. Side driving force does not mean side driving force is not important. In some specific circumstances, side force can become the major driving force to you. Based on the mixture coupling theory, we have extended Darcy's laws, which has been widely used in the geoscience and water science. And we have included the Fick's laws, and we have extended the Freir's laws by incorporating the different components coupling influence. For example, the Darcy's law we have included in osmosis function. Osmosis function is significant in very low permeability porous media. So for example, for the materials such as clay and shale, which we widely use for the water treatment and also for the geotechnical engineering, and we can use such kind of law into the clay. So the theory, the mixture coupling theory is based on the mixture theory, which was developed by use for biological tissues. And based on the further principles of the non-equilibrium thermodynamics, and we have developed a new theory named as mixture coupling theory. And for this theory, it will provide more realistic prediction. We have coupled formulation. You can see the formulation looks a bit complicated, but they are realistic. And we can have a no carbon design because we incorporate every aspects, and we can optimize the every aspects, and we can have a more resilient design. So this is about the theory. And for the multiphysics modeling, we give one simple example. If we want have unsaturated rock in the meter, and we have water transport, we have chemical transport, and we have temperature gradient as well. So this was recently published on IJES, and the acceptance rate is 7%. So we can study the pressure change inside the porous media, and we can study the displacement change in the porous media, and they are coupled with each other. And in the meantime, we can give a prediction of the chemical concentration and the temperature changes. We have physical physics modeling, and we have AI. AI has been traditionally criticized about it's a black box and no physical meaning in AI. What we are trying to do is to develop physics-informed AI rather than classic AI. So we have a few projects. So this project is a physics-informed deep learning for groundwater prediction. It's funded by LUC, and we have a PhD student working on this field, and this is our team from the UK and the Netherlands. We have recently got good results. This direction, because our traditional model, it takes quite a long time for large scale simulation. For example, in Netherlands, it takes about 6 months to get a good result but after 6 months, everything changes. And also there's a highly nonlinear process. So therefore, for the current model, there's a disadvantage, and we will need to use AI to give a prediction. For the groundwater pollution, we have adopted this image process, and we obtained some results which we are going to submit for publication shortly. Another project is physics-informed deep learning for runoff prediction, and we are trying to engage surface water and groundwater together. So this is about the runoff prediction. For the runoff prediction, this paper was led by our PhD student Xiaohui, and we are in collaboration with the CESTEC. We have colleagues over there, and we got one paper published on Journal of Hydrology this year. So the results up to date for the modeling for the deep learning process, we selected 2 locations in United States and using different type of models and scenarios. So you can see for the final results, the highly nonlinear process, the simulation and the prediction from the modeling is very good. Well, this is just a start of a piece of work. And there's another importance I have to mention. When we do the data driving process, how to select the data and how to understand the interactions of this data and make some data links to what the results you need. For example, if we want to give a prediction about our daily activities, we can select the people around you, and we can select your daily routine, and we can select your boss daily routine. All this may have an influence, but some data presented in the system in the training process may become noise rather than real data. So that for the selection process, we will need to engage the physical understanding of this system rather than only rely on machine learning, rely on big data. So that is what we have found.
So, sorry for interruption. You have like 1 minute left.
Yeah.
Sorry.
Yeah, just nearly finish it. And for our group, we have currently 11 PhD students and 2 postdoctors. And in terms of flooding control, we actually trying to break the chain, because the flooding somehow is related to the upstream about the agricultural soils, and they are not able to absorb most of the waters. So therefore, abundant water come to the downstream and from the flooding. So we are recruiting a PhD student in this direction for the natural process-based flooding solution. And in terms of the whole picture structure, what we are trying to do is from the lab scale, we have physical and chemical deep understanding in terms of the capital process and the forms the well-constrained theory. And based on this theory, we are going to study the uncertainty. But uncertainty is a deadlock, because uncertainty, there's quite a lot of things we don't know deep underground. That is why we have to engage with artificial intelligence. But based on what we have understand from the mechanism, and this will provide support for us to explore the physics-informed intelligence. Thank you. That's it, and that's everything from me.